Dated June 25, 2026. Act 1. The physics of the problem. Every time a commercial aircraft takes off, it burns roughly 1 gallon of jet fuel per second. A single transatlantic flight consumes 6,000 gallons. The global aviation industry burns through 100 billion gallons of jet fuel every year. That number is not going down. Air travel demand doubles every 15 years. The carbon inside that fuel came from the ground. It was buried there over 300 million years. When it burns, it goes into the atmosphere in roughly 4 seconds. We have spent the last century digging up that carbon and releasing it faster than any natural process can reabsorb it. The question this documentary asks is simple. What if we ran that process in reverse? What if instead of digging carbon up from the ground, we pulled it out of the air, combined it with hydrogen split from water, and built the identical hydrocarbon molecules that power every jet engine flying today? No new engines, no new aircraft, no new infrastructure at the airport, just different fuel. That fuel exists. It is called synthetic ESCF, Electro-Sustainable Aviation Fuel. A company called 12, operating a production facility in Moses Lake, Washington, is making it right now using a process called PM co-electrolysis. They pass electricity through a membrane that simultaneously splits water into hydrogen and reduces captured carbon dioxide into carbon monoxide. Those two gases combine into synthesis gas. Synthesis gas, through the Fischer-Tropsch process, becomes jet fuel, chemically identical to petroleum-derived jet fuel, certified by the FAA, already in commercial use on Alaska Airlines flights. But here is the constraint that defines everything else in this story. Making 1 gallon of synthetic jet fuel requires approximately 70 kilowatt-hours of electricity. That is not an engineering inefficiency. That is a thermodynamic law. The Gibbs free energy required to reverse combustion, to climb back up the energy gradient from carbon dioxide and water to a high-energy hydrocarbon, is fixed by physics. You cannot engineer your way around it. 70 kilowatt-hours per gallon is the floor. At Moses Lake, that electricity comes from Columbia River hydropower at 3 cents per kilowatt-hour. The all-in production cost today is $8.80 per gallon. Conventional jet fuel costs roughly $3 per gallon. That gap, $5.80, is the only number that matters in this documentary. Everything that follows is the story of how that gap closes. Act 2. The economics of the mandate. In August 2022, the United States passed the Inflation Reduction Act. Buried inside that legislation is a provision called the 45Z Clean Fuels Production Credit. It pays synthetic fuel producers up to $1.75 per gallon for every gallon of eSAF that meets a life cycle carbon threshold. It runs through 2027. In Brussels, the European Union passed Refuel EU Aviation. Starting in 2025, every fuel supplier serving an EU airport must blend at least 2% synthetic SAF into their supply. That mandate climbs to 6% by 2030, 20% by 2035, and 70% by 2050. Non-compliance carries financial penalties enforced at the airport gate. Those two policies do something specific. They do not make eSAF cheap. They make the market captive. Airlines operating into Frankfurt, Amsterdam, and Paris cannot avoid the blending requirement. They have to buy the fuel regardless of the price premium. That creates a guaranteed revenue stream for synthetic fuel producers before cost parity is ever achieved. This matters because it changes the investment logic. When you have a guaranteed offtake market, you can finance a large-scale electrolyzer plant. When you can finance the plant, you can reach the scale at which unit costs fall. The mandate doesn't solve the economics. It funds the learning curve that eventually does. The 45Z subsidy at Moses Lake effectively brings the production cost from $8.80 down to $7.05 per gallon. Still more expensive than petroleum. But the EU mandate creates a premium market willing to pay it. The arbitrage between mandate-driven European demand and subsidized American production is the business model that keeps the industry alive long enough for the real cost reductions to arrive. Act 3. The technology advantage. Not all synthetic fuel pathways are equal. 12's one-step PEM-CO electrolysis approach holds a structural advantage over the most common alternative. The two-step pathway splits water first to make hydrogen, then runs a separate carbon dioxide reduction unit, then combines the outputs. Each step has its own efficiency loss. The one-step approach does both simultaneously inside a single membrane, eliminating one full processing stage and the capital cost that comes with it. The primary technical constraint on scaling PEM-CO electrolysis is a single element on the periodic table, iridium. At the anode of a PEM electrolyzer, the membrane operates in a highly acidic, highly oxidizing environment. Only iridium can survive that environment at scale. Iridium is one of the rarest elements on Earth. The entire global annual supply weighs less than 4 metric tons. You cannot build a fuel industry on 4 tons of raw material. This is the bottleneck that changes the entire cost trajectory of the industry. And it is the bottleneck that artificial intelligence is solving right now. Act 4. The AI engineer. For over a century, controlled stellar physics, the concept of a star in a jar, has represented the ultimate clean energy vision. The fundamental challenge has never been understanding the physics of the star. It has been engineering the jar, magnetically confining 100 million degree plasma, drilling miles into basement granite, designing catalysts at the single atom scale. These are multivariable engineering challenges that traditional trial and error science cannot solve in any realistic time frame. Artificial intelligence serves as the engineer that finally makes the jar work. In December 2023, Google DeepMind published results from a system called GNOME, Graph Networks for Materials Exploration. Using graph neural networks to calculate quantum mechanical crystal stability at scale, GNOME expanded humanity's known catalog of stable materials from 48,000 to over 2.2 million in 12 months. The entire prior history of materials science had found 48,000 stable crystals. One AI model found 2.2 million more. Microsoft Research followed with MatterGen, a generative diffusion model that doesn't screen existing materials but designs entirely new ones to specification. You give it target properties, high electrochemical stability, low iridium content, resistance to acidic dissolution. It outputs candidate crystal structures that satisfy all three simultaneously. Lawrence Berkeley National Laboratory built A-Lab, an autonomous robotic facility that takes candidate compositions from models like Genome and MatterGen and physically synthesizes them without human intervention. Robotic arms prepare chemical precursors, execute the synthesis, and run X-ray analysis to validate the result. The cycle from candidate to validated physical sample runs in under 12 months. The specific output relevant to this story, AI frameworks have isolated stable manganese antimony oxide and ruthenium titanium oxide solid solutions that can replace iridium at the PEM anode. By doping ruthenium, which is cheaper and more catalytically active but naturally unstable, with AI-selected titanium or cobalt crystal cages, researchers have achieved a 90% reduction in iridium loading while maintaining equivalent catalytic performance. The bottleneck that threatened to cap the entire industry is being dismantled at the atomic level. The membrane problem is being solved simultaneously. Traditional Nafion membranes degrade under hydroxyl radical attack, the membrane equivalent of rust. AI molecular dynamics models have mapped the exact degradation pathways and designed perfluorinated sulfonic acid membranes reinforced with cerium oxide radical scavengers that extend operational lifespan past 100,000 hours. These are not projections. These are peer-reviewed results in Nature and Science from Lawrence Berkeley, DeepMind, and Microsoft Research, published between 2023 and 2025. Act 5. The energy beneath our feet. Solving the catalyst problem reduces the capital cost of the electrolyzer. But the dominant variable in the production cost equation is still electricity. 70 kilowatt-hours per gallon multiplied by the electricity price determines the floor. At 3 cents per kilowatt hour, that's $2.10 of the $8.80 production cost. At 1 cent per kilowatt hour, it falls to 70 cents. The path to 1 cent electricity runs through two technologies. One is already operating commercially. The other is approaching its first commercial milestone. Fervo Energy operates enhanced geothermal systems, EGS, by drilling into hot, impermeable basement granite, fracturing it hydraulically to create an artificial heat exchanger, then circulating water to harvest thermal energy. The geology is available almost everywhere on Earth. The barrier has always been drilling cost. Granite destroys conventional drill bits. Fervo deploys physics-informed machine learning integrated with distributed fiber optic sensing arrays inside the wells. The AI processes real-time torque, mud flow, and weight-on-bit data every second and outputs optimized drilling parameters that keep the bit operating within safe resonance limits. At its Cape Station project in Utah, this reduced drilling time by 49% and cut per well capital cost from over $11 million to under $5.5 million. That cost reduction directly translates to cheaper electricity. Fervo is producing geothermal power at an estimated 2 cents per kilowatt hour. Continuous, 24 hours a day. No weather dependency, no grid wheeling charges. Quaise Energy is working on the next order of magnitude. Their technology uses a gyrotron, a vacuum electron tube originally developed for fusion research, to beam millimeter-wave electromagnetic energy down a borehole, vaporizing granite without mechanical contact. The vaporized rock is purged to the surface. The chamber walls vitrify into a glass ceramic casing. The system targets depths of 15 to 20 kilometers, nearly double the deepest mechanical wells ever drilled, reaching ambient rock temperatures between 400 and 500 degrees Celsius. At those temperatures, water enters a supercritical state, carrying 10 times more thermal energy per unit mass than standard steam. Quaise projects levelized electricity costs of 1.5 to 2.5 cents per kilowatt hour at commercial scale. The commercial timeline runs from 2029 to 2036, conditional on waveguide durability at depth. Act 6, the star in the jar. The third energy technology in this story does not draw on anything buried in the Earth. It recreates what happens inside the sun. In nuclear fusion, two light hydrogen isotopes, deuterium and tritium, are compressed and heated to 100 million degrees Celsius. At that temperature and pressure, the atomic nuclei overcome their electromagnetic repulsion and fuse. The mass of the resulting helium nucleus is slightly less than the combined mass of the inputs. That missing mass converts directly to energy under Einstein's E equals mc squared. The energy density is roughly 4 million times greater than burning coal. The challenge is the jar. Containing 100 million degree plasma requires magnetic confinement, a precisely engineered magnetic field that keeps the plasma core from touching the reactor walls. For decades, managing that magnetic field was beyond the resolution of human operators. The plasma is dynamic. It wants to destabilize. Magnetic instabilities called neoclassical tearing modes and edge-localized modes can dump the entire plasma energy load into the reactor wall in milliseconds. In 2022, DeepMind published results from a collaboration with the Swiss Plasma Center at EPFL. A deep reinforcement learning system was trained to control all 19 magnetic coils of the tokamak configuration variable simultaneously. The AI outputs magnetic field adjustments every 100 microseconds, too fast for any human controller. It holds, stretches, and shapes the plasma into stable configurations that conventional controllers could never maintain. Commonwealth Fusion Systems is building Spark, a compact high-field tokamak using high-temperature superconducting magnets that achieve magnetic field strengths previously requiring an entire building of conventional electromagnets. CFS projects first plasma in 2025, with commercial power delivery beginning in the early 2030s. When fusion reaches industrial scale, and the probability-weighted timeline puts that between 2033 and 2037, it delivers electricity at a projected cost of 1 cent per kilowatt hour or below. Behind the meter. Continuous. From a facility with a parking lot footprint. At 1 cent per kilowatt hour, with a $1.55 non-electricity stack, the all-in production cost of synthetic jet fuel reaches $2.25 per gallon. Cheaper than petroleum, without any subsidy. That is what a star in a jar does to the economics of aviation. Act 7. The cost curve. Here is the integrated model, probability weighted across all 4 technology vectors. In 2026, using Columbia River hydropower at 3 cents per kilowatt hour, with today's iridium-dependent capital stack at $6.70 per gallon non-electricity cost, the all-in production price is $8.80 per gallon. By 2030, AI materials research eliminates iridium dependency. The non-electricity stack drops to $2.70. Optimized solar PV at co-located desert facilities provides electricity at 2.5 cents per kilowatt hour. All-in cost, $4.45 per gallon. By 2035, Fervo-class AI-optimized EGS provides continuous industrial baseload at 2 cents per kilowatt hour. The iridium-free capital stack matures to $1.55. All-in cost, $2.95 per gallon. The $3 conventional jet fuel parity line is crossed. By 2040, early fusion grid delivery and behind-the-meter solar combinations push industrial electricity to 1 cent per kilowatt hour. The capital stack holds at $1.55. All-in cost, $2.25 per gallon. Synthetic eSAF is definitively cheaper than petroleum refining economics, independent of any subsidy regime. The base case prediction? By 2036, there is a 65% probability that unsubsidized synthetic eSAF reaches price parity with conventional jet fuel, conditional on iridium-free catalyst validation by 2028, EGS wells at $4.5 million by 2030, and the EU 5% eSAF sub-mandate enforced through 2035. The optimistic case, parity by 2033 with an 85% confidence interval if Quaise Energy validates supercritical deep geothermal by 2031 and the 45Z framework is extended through 2035. The pessimistic case, parity delayed past 2045 if early tax credits expire prematurely, raising project financing costs above 9%, or if alternative catalysts fail to match iridium's operational lifespan under dynamic cycling. The single most important variable in the pessimistic scenario is not technology. It is capital. An electrolyzer plant built at 9% cost of capital produces fuel that is $1.20 per gallon more expensive than the same plant built at 5%. Policy continuity is not optional. It is load-bearing. Act 8. The geography of power. Chemistry does not care about geography. There are currently 47 nations on Earth with 0 domestic fossil fuel production. For every one of them, energy dependency is not an abstraction. It is a balance of payments problem, a defense vulnerability, and a constraint on every sovereign decision their governments make. A maritime blockade, an OPEC production cut, or a pipeline dispute in a neighboring country can immediately destabilize domestic inflation and paralyze military logistics. Japan imports 99% of its fossil fuels. Those imports travel through the South China Sea on maritime routes that are increasingly contested. Japan has abundant offshore wind, geothermal resources, and existing nuclear baseload. One co-located synthetic fuel facility, drawing on that electricity, can produce domestic aviation fuel from air and seawater. The molecules are identical. The aircraft cannot tell the difference. But the geopolitical exposure is gone. Under the NATO single-fuel policy, all Allied military aircraft are required to operate on the same jet fuel specification. The Netherlands government has already integrated eSAF production into its NATO aviation readiness framework. That is not a sustainability initiative. That is a fuel sovereignty initiative inside official defense readiness doctrine. The distinction matters enormously. For over a century, the global balance of power has been tied to geological chance. Nations that happen to sit atop ancient marine sediments held disproportionate influence over global transportation, industrial production, and military mobility. The transition to synthetic power to liquid fuels is a structural realignment of that architecture. It moves energy production from resource extraction to chemical engineering. If a nation has access to water, air, and electricity, it can produce its own aviation fuel domestically. Fuel availability is no longer a function of what is beneath the ground. It becomes a function of what a nation can build above it. Act 10. The Industrial Transition. Understanding how a fuel industry transitions from fossil to synthetic requires understanding what is actually being replaced. The global petroleum aviation fuel supply chain is one of the most capital-intensive industrial systems ever built. It consists of approximately 800 active oil fields extracting crude, over 700 refineries converting it into jet fuel, a network of roughly 400,000 kilometers of product pipeline, and 11,000 commercial airports with fueling infrastructure built around liquid hydrocarbon delivery. The replacement value of that infrastructure exceeds $3 trillion. Synthetic eSAF does not replace that infrastructure. It uses it. Because synthetic jet fuel is chemically identical to petroleum-derived jet fuel, same molecular weight distribution, same energy density, same viscosity profile, it can be blended into existing storage tanks, pumped through existing pipelines, and dispensed through existing airport fuel systems without modification. The infrastructure transition cost is not $3 trillion. It is close to zero. What changes is where the molecules are manufactured. Instead of an oil field in Saudi Arabia or the Permian Basin, the manufacturing site is a chemical plant located next to a geothermal well or a fusion reactor. Instead of a refinery cracking crude into fractions, it is an electrolyzer array synthesizing hydrocarbons from first principles. The product at the end of the pipe is identical. The supply chain upstream of the pipe is entirely different. This matters for how we think about the speed of transition. Technology transitions that require replacing installed infrastructure, like the shift from internal combustion vehicles to electric vehicles, which requires new charging networks, new battery supply chains, and new manufacturing lines, move slowly because the replacement cost is enormous. The transition to synthetic aviation fuel faces almost none of that friction at the consumption end. Airlines do not need to buy new aircraft. Airports do not need to build new fueling systems. Passengers do not experience any change whatsoever. The friction is entirely on the production side, building enough electrolyzer capacity to supply an industry that consumes 100 billion gallons per year. At current electrolyzer manufacturing rates, that would take decades. But electrolyzer manufacturing is itself on a steep learning curve. Electrolyzer costs have fallen 65% since 2015. Every gigawatt of deployed capacity brings the next gigawatt cheaper. The transition is not a cliff to jump off. It is a ramp to climb, and the slope of that ramp is determined by how aggressively capital follows the policy signal. The EU mandate is that signal. The 45Z credit is that signal. The NATO fuel sovereignty doctrine is that signal. When policy creates a guaranteed market, capital follows. When capital follows, manufacturing scale increases. When manufacturing scale increases, costs fall. The ramp steepens. There is one more dimension of the industrial transition that rarely appears in energy analysis jobs. The petroleum refining industry employs approximately 500,000 people globally in highly skilled, well-compensated technical roles. Electrolyzer manufacturing, operation, and maintenance requires a comparable skill set. Chemical engineering, process control, materials science, high-voltage electrical systems. The workforce transition is not a destruction of industrial employment. It is a relocation of it, from extraction geographies to manufacturing geographies. For nations without domestic fossil resources, that relocation is entirely welcome. For nations that currently export fossil fuels, it represents a structural economic challenge that no amount of optimism about synthetic fuels should minimize. The honest acknowledgement of that disruption is part of a complete analysis. The technology works. The economics close. The infrastructure transition is manageable. The workforce disruption is real and requires deliberate policy to address. The story of synthetic aviation fuel is not a story about the end of industrial civilization. It is a story about its continuation, under different chemistry, at different latitudes, with different geopolitical consequences. Act 11, the closing argument. This documentary is a prediction, not a promise. The technologies described here are real. The cost curves are built from peer-reviewed data, published engineering parameters, and publicly available project deliverables. The organizations named 12, Fervo Energy, Quaise Energy, Google DeepMind, Microsoft Research, Lawrence Berkeley National Laboratory, Commonwealth Fusion Systems, are independent commercial and research institutions operating entirely outside this production. Their work is their own. The synthesis presented here, the quantified connection between AI materials discovery, deep geothermal, fusion plasma control, and synthetic fuel economics, is the contribution of this documentary, documented and dated June 25, 2026. The predictions carry confidence intervals because they are honest. A 65% probability is not a guarantee. The DAC cost reduction to $100 per ton carries a 55% on-time probability. First fusion grid delivery carries 40%. These are not failures of optimism. They are accurate representations of where the engineering stands. But here is what is not uncertain. The thermodynamic law is fixed, and the direction of the cost curve is established. The gap between $8.80 today and $2.95 in 2035 is not a speculation. It is a calculation built on already demonstrated milestones. The iridium replacement work is in the literature. The Fervo drilling cost reduction happened. The DeepMind plasma control result was published in Nature. The only question is timing. We have spent the better part of a century operating under a simple geopolitical reality that the lifeblood of global commerce must be dug out of the earth, fought over, and transported across vulnerable oceans. We accepted the idea that energy was a lottery ticket, one that some nations won by geography and others lost by default. But chemistry does not care about geography. The carbon atoms required to lift a 300-ton aircraft into the stratosphere are all around us, floating in the wind, waiting to be organized. The only thing missing was the raw, unyielding power needed to break those molecular bonds and build them back up again. For the first time in history, we are learning to capture and control the energy of the stars, using artificial intelligence to manage the magnetic fields needed to hold it in place. We are learning to drill into the heat of the Earth using the same electromagnetic technology built for fusion reactors. We are learning to design catalysts at the single atom level in robotic laboratories that never sleep. We are, for the first time, learning how to build a star in a jar. And once the jar works, we can finally harvest the wind, bottle the sun, and make our fuel from the air. End. Methodological disclaimer. Dated June 25, 2026. This script has been constructed as an independent, third-party synthesis of emerging energy research trends. All corporate entities named herein, including 12 Benefit Corporation, Fervo Energy, Quaise Energy, Google DeepMind, Microsoft Research, 1.5, Lawrence Berkeley National Laboratory, and Commonwealth Fusion Systems are independent commercial and research institutions operating outside this production framework. Their inclusion illustrates specific technical approaches. This documentary's contribution is the synthesis, the quantified connection between these independently developed technologies and their combined effect on synthetic aviation fuel economics through 2040. Cost model inputs draw on public data from the National Renewable Energy Laboratory, the International Renewable Energy Agency, and peer-reviewed chemical engineering literature.